So this leaves only one more script for us to review before we have a fully functioning anti-aircraft gun. And this is bullet nav. And as we have seen, bullet nav is attached to the actual projectile itself, which in our case is this bullet prefab, which, as I mentioned in the last video, is really the only object I've borrowed from this Kawaii Tanks project. And the reason that it made sense for me to borrow this was because I have made pretty extensive use of the most important component of this project in some of my other games, which is this fairly detailed animated tiger tank. But if you have no use for a tiger tank model in any games that you're building, then it probably doesn't make sense to download and master all the pieces of the Kawaii Tanks project just for a prefab of a projectile to use for this gun. You can easily make one yourself. I mean, all you need really is a small cylinder, or really any primitive shape, that has a rigid body and a collider attached to it. I like this primarily because of it has some trails attached as well, some particle effects, and you can learn how to, do those too if you want. But again, it would be easy enough to simply fabricate your own prefab, but to it, you would definitely want to attach some kind of script that was analogous to this bullet nav script. And, why? Why do we need to have intelligence in the projectile itself? Well, as we have seen, at a minimum, we need it because we need to be able to set the lifetime of this script so that that's the proximity fuse, so the shell knows when to explode. But as we'll see in here, it's also very often the case with a projectile that it needs to have other intelligence as well, so that it knows what to do if it impacts on something. And while I have taken about 90% of the functionality out of the Kawaii Tanks project's own bullet nav script, which they called bullet nav_cs, I've left enough in there just to give you some sense of other things you could do with a projectile if you weren't simply using it in an anti-aircraft context. But that is going to be our focus here. So I should note probably too, if you're not familiar with Visual Studio Code as a code editor, there's a native code editor in Unity that works quite well. I had used it in versions prior to 2017, but I discovered recently that Microsoft has released this essentially free, somewhat lightweight version of Visual Studio, which, one, is free as opposed to the quite expensive package you need for Visual Studio. Two, is considerably more lightweight, easier on your CPU, but still comes with most of the IntelliSense features that you get in Visual Studio itself. I'm a big fan in general of free software. Unity itself is free. All the screen capture, the video editor I've used to edit these videos, that's all mostly open source. It's all freeware. And Visual Studio Code, just search for it online, is also free. Big fan of that. So, bullet nav. And again, this is a very simple script, 35 lines total, and the original one from the Kawaii Tanks project was quite a bit longer. I stripped most of that out. So we are declaring a float lifetime, which is, of course, the all-important proximity fuse time setting. It has to be public so that it can be called or set from a different script. And then there is a public game object, broken object, also declared here, because just as we are setting the prefab for bullet from Firespawn, so within the bullet script itself, we're having to set its broken object, which is going to be what happens when it breaks or explodes. So in my case, I've loaded in this detonator for that nice explosion that we've seen, which, by the way, doesn't come from the Kawaii Tanks project, but from something called the Detonator Explosion Framework, also free from the Unity Asset Store, and certainly worth exploring for any game where you're blowing stuff up. So we've loaded that in as our broken object. Transform this transform. There's a boolean is live, and we'll see where that comes into effect, which is rare, but I'm setting it to true to start with. So on start, we're just going to set this transform to this dot transform, and then we're going to go ahead and invoke the function hit, which is down below. We'll look at this function hit in a moment. First of all, though, what is invoke? Very useful little function which allows you to call another function in the same class within the same script, and rather than calling it instantly as it would if I were to just say hit, I can say I want you to wait this interval of time in seconds and then call this function. So this, of course, is lifetime. So basically I'm saying, by way of my proximity fuse functionality, I'm saying wait this amount of time and then call this hit function, which is essentially just going to cause the shell to detonate in our case. So first it's going to test if we've loaded the broken object in, and if we have, we're going to go ahead and instantiate that right at the position and the rotation of this shell itself. And then I'm going to go ahead and destroy this shell so that in effect I am more or less instantaneously replacing the shell with the explosion. So there's our detonation. And that really is all the functionality of this script in about 99.99% of the cases. There is going to be a very rare case, but it's still possible, when on collision enter comes into the picture. This was something that they had as part of the much more elaborate Kawaii Tanks project version of this bullet nav. And I left it in to allow for the very rare case when the shell that I've fired actually collides with the jet and collides with it, before it has a chance to explode. I'm certain that even with any number of flat guns set up, I could blast away at that jet all day and probably never actually directly collide with the jet itself. But in the case I did, I would like it to do something. I'd like it to go ahead and explode in that case as well. So if is live, which we saw above, is set to true, then the first thing we're going to do is set is live to false, so that this, once it hits any collider of the jet, it basically goes ahead and explodes. It doesn't continue on and do anything else. And then we're going to call hit, which, as we've seen, is just going to cause it to explode. So that takes care of, in my game, the last 0.001% of cases where we've actually collided with the jet rather than exploding as close to it as our calculations allow us to. Now, they've got a fixed update in here, which I've kept in just with this comment to show you that this can contain code for raycasting to determine proximity to an impactor and how the shell should respond. So if you were using this in a situation where you weren't trying to shoot planes out of the air and therefore relying on airbursts, but were actually using the gun as an impactor, even if I were using the same basic kind of tower attack game or tower defense game, and instead of a plane, there were, let's say, waves of slowly advancing tanks that I had to try to shoot. In that case, I would want to use my shell as an actual impactor. And if I was to do that, then I might want to have some logic in here to determine, first of all, are there collisions that I want to ignore? Are there things that I want my shell to just plow through without exploding and, destroying itself? And second, I might want to, because if I had tanks and they would be armored, I might want to determine, what's the angle at which my shell impacts against a surface. And if that angle is not close enough to perpendicular, then I might want the shell to simply bounce off. And you would do that with I think it says here down here, hit normal, which is a property that raycasting can return, where the normal tells you exactly at what angle you've hit the surface. And so therefore, you can use logic in there to determine bouncing off or deflection if that's what you want to do. That is well outside the scope of this demonstration. I simply wanted to indicate that the bullet nav script can have a lot more intelligence than I need it to have in my particular case. But with that said, the way it's coded now, this will function perfectly well as an anti-aircraft gun. And we now have enough code, as we've seen, to allow this gun to acquire a target, to aim at the target, to calculate where it thinks the target will be, even when it's moving quickly in a certain direction, to fire shells automatically, correctly fused to explode at the right time, and then for the shells to actually explode. And that concludes this demonstration.